All right, I know I stand between you guys and pizza and beer, which is an unenviable place to be, so hopefully we can breeze through this. This challenge differs from standard DREAM challenges where we're really interested in the predictive models. Here we're more interested in what we're calling digital biomarkers, or in other words, how do you process data coming from these mobile sensor devices like phones and watches. Really, we sort of see the machine learning portion of this as just a detail in the scoring, but it's really these features that we're most interested in that then might have some clinical utility, we're hoping. So in this case, we had for both sub-challenges, we had a training and a test data set. That's pretty standard. We actually had participants submit extracted features on both the training portions and the test portions. We used the training portions to fit models using just a standard machine learning ensemble model, and then we predicted with their test features to come up with a score. And because we've asked for these features for all of the data, even including data that we didn't use to score, we really hope that we're going to have a really rich and interesting community phase. So the first data set is from the mPower study, which is a research kit study. It's an observational study, so anyone could join. Anyone with an iPhone can download this app and join the study. It measures passive structured activities and survey information about 4 dimensions of Parkinson's disease. It also collected some basic information about diagnosis, whether or not they were diagnosed with Parkinson's, the year, and all structured activities ask for information about where they are in regards to their medication. We're going to focus for this challenge on the walking activity, which studies gait and balance. So the Gait and Balance Test is a pretty basic test. You're asked to put your phone in your pocket or in a bag, walk for 20 seconds, turn around, stand for 20 seconds. So the phone reads the accelerometer and gyroscope data during all this time. These are the tests that have been performed. Luckily, we were sort of naturally split into a training and a test set. A portion of the first 6 months of the data had already been publicly released. That was our training set. There was another portion from the first 6 months that hadn't consented to be shared broadly, as well as an additional 18 months of data that had not yet been released. So the objective of this challenge was to extract features from the mPower mobile walking and balance test, which can be used to distinguish Parkinson's patients from controls. So here are some details. We asked participants to submit features for both the training and test set. I already covered that. We did the model fitting, performed the predictions, and scored the models. We only used a subset of the data for scoring in order to roughly balance ages for cases and controls, for example, so that age wasn't a dominating predictor. For this case, we only used Parkinson's patients that were off medication, so presumably in their worst possible state. Obviously, we might like to go back and look at how it does with Parkinson's patients who are on medication. Because each individual may have multiple tests, we summarized so that each individual was only present once in the training and the test data, and we fit a basic ensemble model for each set of features we received. So the second data set is one that Mark alluded to that was sponsored by the Michael J. Fox Foundation. This is a study of whether or not wearable sensor data can be used to assess symptom severity in patients who experience motor fluctuations. So what does that mean? Not all Parkinson's patients are well controlled by their medication. So there tends to be a bit of a curve, both when they take their medication and when they come off it. So here's a patient who's off their medication. They take their medication, and while their tremor decreases, there is an onset of dyskinesia, which is involuntary motor movements. In this study, participants had smartphone watches on each wrist and a smartphone at their waist. We only used the in-clinic data, which is structured like this. They came in for 2 separate visits. On the first visit, they came medicated, and then they performed tasks throughout the day as their medication wore off. On the second visit, they arrived off medication, performed some tasks, and then took medication later in the day. So they performed a similar sequence of about 8 tasks in multiple cycles throughout this day. So there are multiple observations of each of the tasks over 2 different days. For each time a task was performed, all limbs were scored with respect to tremor, dyskinesia, and bradykinesia. So for each test, we have a corresponding score of each of these 3 symptoms. We derived 3 sub-challenges based on the L-Dopa data. One was to extract features based on upper limb tremor when a task's being performed. The second is to identify features that predict upper limb dyskinesia for a limb at rest. So in this case, we used single hand tests like finger to nose or alternating hand movements, but we used the hand that was not actually performing the task. The third was to estimate upper limb bradykinesia in the active limb. And you could see a set of example tasks that were used. So very similar to the mPower data, what do I want to say here? So here, each individual task is the unit that we're measuring because we have individual measurements on each task. Though we were sure to split the training and the test data so that if one task for an individual fell in the training data, all their tasks fell in the training data and vice versa, so that to avoid learning on individuals. And again, an ensemble model was fit. AUPR was used to rank the features. The challenge timeline was something like this. We released the mPower data in July and had a deadline in October. The L-Dopa data was released a little bit later. We just closed in early November. Here we are at the DREAM workshop, and we're about ready to launch the community phase. We haven't yet scored the L-Dopa data, so I won't share any of those results today. We had about 450 registrants all over the world on 6 continents, so that was pretty exciting. All in all, we had about 38 unique teams across the 4 sub-challenges. So these are the results. My slide is not showing up that well, so I apologize for that. These are the results for Subchallenge 1, the bootstraps. On the bottom in red is the clinical-only model. You can see that almost all of the submissions outperform the clinical-only model. And in fact, a large portion of the submissions outperform our top dry run model, which had an AUROC of about 0.65, sorry, about 6.5, which would be here. But we noticed something really interesting in these results when we started reading the write-ups. It had to do with this submission here, where this team actually only used metadata. They didn't actually use any of the mobile sensor data. And when we went to look back in the data, we found an artifact relating to the date that a test was performed. And so these are histograms of the date a test is performed, split by cases on the top and controls. And especially in the test cases, you can see that, in the test data, you can see that cases tended to perform tests much later than controls. Incidentally, the big spikes correspond to an announcement by Apple. So these are all Apple devotees downloading the data. Looking at it a different way, when we summarize these file handles, or which are integers correlated with date, we can see a strong difference, a statistically significant difference between cases and controls, both in the training and test data. So we took a subset of the data that matched these file handle IDs so that there was no statistical difference between cases and controls. We wanted to see how many models were affected by this artifact. So we rescored in this subset that lacked the artifact to make sure that at least our winning models were doing well. And you can see that the landscape changes pretty dramatically. Our top models stayed our top models, but below that, the models changed in rank pretty substantially, and now only about 14 of them are doing better than our clinical-only model. And in fact, what would have been our second place dropped almost to the bottom. So if you're interested in what sort of methods are being used in these top models, we see some neural nets, some signal processing, some wavelets. As I said, I won't go into all of the potential analyses, but we're about to kick off the community analysis phase. Because we have these really rich features as submitted by the participants, we can ask a wealth of data, a wealth of questions, especially in the mPower data that is a really rich data set. So in conclusion, mobile sensor data can distinguish between normal and Parkinsonian features in a walking test. The best methods tend to employ deep learning or neural net models, and we'll hear from two of those in a moment. I can give you a little preview of the Subchallenge 2 results. We are seeing good evidence to predict symptom severity in the L-Dopa data, and we'll release the information on winners as soon as we validate them. With that, I'd like to thank our excellent dry run team, our excellent organizing team, which spanned a number of public and private institutions, Early Signal, Harvard University, University of Luxembourg, University of Rochester, UW, and Verily. And from SAGE, I'd like to acknowledge co-leads Larson and Lara, and then our excellent data scientists, Yudi and Phil. And most importantly, we've had really great support from our funding agency, Michael J. Fox. They've been really active, engaged, and supportive, and so glad to have Mark here. And with that, I'll take questions.